as Nalini said, I am going to tell you in the next 10 minutes what the universe is made of. And on the face of it, that's not such a hard thing to do. You look out, and what do we see? Well, the obvious answer, if you've gone out and you've looked, is we see a whole lot of stars. That's what seems to be out there. Tons and tons of stars. Well, turns out, if you look with a good telescope, you see that there's more going on than that. There's not just stars, there's lots of clouds of gas and dust in between those stars, but okay. Still not that different. And then you zoom out some and you see those stars don't go on forever, just randomly arranged. All the stars that we can see with our naked eye are clustered in a giant group called a galaxy. And our galaxy is called the Milky Way galaxy. It contains billions of stars and giant clouds of gas and dust spread out in between them. Well, then you step back even further, zoom your telescope further into space, and you see that our galaxy is one of many, many galaxies. This is a picture taken by the Hubble Space Telescope, and it is looking so far out into space that each one of those objects is not a star, but an entire galaxy, each one filled with billions of stars. And in each one, there are these gigantic clouds of gas and dust where new stars are continually forming. And it turns out there are also giant clouds of matter in between those galaxies. But the most remarkable thing about all of this is that you look out and you measure the detailed properties of the light coming from all these things, the stars, the dust, the gas. And what you find is, based on that light, it's all made of the same stuff that we are. We are made of carbon, nitrogen, hydrogen, oxygen, but that in turn, those are all kinds of atoms. It's all made of three particles, protons, neutrons, and electrons. Everything I've just talked about, everything you see in these pictures, the stars, the dust, the gas, it's all made of those same three particles that you're made of, protons, neutrons, and electrons. It gives you this nice, warm, fuzzy feeling that you're part of something big. And I'm going to spend the rest of my 10 minutes stripping that warm, fuzzy feeling away from you. It turns out that that's what we see when we look out, and that's not really what most of the universe is made of. And the way this was discovered, everything I've said so far, that there are galaxies out there and so on, we've known that for just about 100 years. But in the 1970s, a woman named Vera Rubin was studying some of the detailed properties of those galaxies. And what you see when you look at galaxies, they're all rotating, like giant solar systems. All the stuff in the galaxy is spinning around the giant mass of stuff at the center. And I've drawn that in with these little arrows, and Vera Rubin took detailed measurements of how fast everything was rotating. And we know the laws that govern that. Newton's laws, or going back further, Kepler's laws of planetary motion. They work in our solar system. They tell you how fast everything should be going, and it depends on how much mass is in there. And what she found is it didn't match. If you calculate, you look at all the stars and dust and gas you see there, you figure out how much of a gravitational pull would that be exerting, and figure out from that, how fast should a star here be rotating, how fast should a star here, how fast should some gas there. It doesn't match the data at all. So you're led to conclude one of two things. Either Newton's laws are wrong, and we have lots of reasons for not coming to that conclusion, or there's a whole lot more mass in there than we thought. Which really means there's a whole lot more mass in there than we can see. The stars, the dust, the gas, all the things that make up the part of the galaxy that we can see with any of our measuring devices, turns out to be about 10% of what's in there. And the rest of it got called dark matter. Every galaxy, virtually every galaxy we see, is surrounded by a halo of dark matter that extends far beyond it, around it, and within it. There are countless dark matter particles streaming through your body at this very minute. It's everywhere inside the galaxy, and there's 10 times as much of it as there is of any of the stuff we're familiar with. And we have no idea what this stuff is. Some unknown kind of particle. People are hard at work trying to detect it. To date, nobody has. All right, so that's kind of weird. The stuff we are familiar with, the particles we know, that's about 10% of all the matter in the universe, but, you know, particles are particles. It's some other kind of particle. To make life weirder, we fast forward and look on an even broader scale. Vera Rubin in the 70s was measuring what was happening within each galaxy. But if you look on a broader scale, you can ask, what are all those galaxies doing together? And the answer is, the universe is expanding. All the galaxies are moving away from all the other galaxies. Every galaxy out there we see, virtually every galaxy we see, is moving away from us and away from each other. And the reason, I can tell you very simply, we have no idea. The reason they're all moving away from each other today is because they were doing it yesterday, and they're still being carried along by that inertia. And the reason they were doing it yesterday is because they were doing it a billion years ago and so on, back to about 14 billion years ago when it all started, and we don't know what started it. But that's not what I'm talking about today. It's all expanding. We know that much. But once it starts expanding for this unknown reason, all of those galaxies exert a gravitational pull on each other that tends to pull them all back in towards each other. So it should slow down that expansion. How much it slows it down depends on how much matter there is. And so people set out to measure that. How much is the rate of expansion slowing down over time because of the pull of gravity? And what they found, which is the answer that nobody expected, is that it's not slowing down, it's speeding up. It's as if I took a ball and I threw it up, and you'd think, oh, well, the pull of Earth's gravity will gradually slow it down and make it fall, but instead I throw this ball up, and the instant it leaves my hand, it starts going up faster and faster and faster and faster out into space. Gravity, as we know it, doesn't work that way. More precisely, the kinds of things that we're familiar with don't exert that sort of gravity. So what we conclude is that there's something filling all of space, everywhere we can see in the universe, that exerts a form of repulsive gravity. And in one of the most unfortunate naming choices in terms of deliberately trying to confuse everybody in the community for decades to come, that was termed dark energy. So, to sum up, here is the answer to the question I started with. 70% of all the energy in the observable universe is dark energy, by which we mean this stuff, whatever it is, that is everywhere exerting repulsive gravity, and we haven't the slightest clue what's doing that. And we know that it's about 70% because it's winning. All the matter, including the dark matter, exerts attractive gravity, and yet things are flying apart faster and faster, so there must be twice as much of this stuff as everything else. About 27% of all the energy in the universe is dark matter, this mysterious kind of particle that we know is around and within all the galaxies streaming through our bodies, and we have no idea what particle it is. And about 3% of the stuff out there in the universe is protons, neutrons, and electrons, these nice familiar particles that make up everything that you and I have ever seen in our lives. And there you have it. And I will leave you with a thought.